Lecture 7 of Module 2 on Research Design and Data Management. We will discuss more about the experimental design and statistical tests. The common designs in biological experimentation include, as we had stated, the completely randomized design. And this is probably the more frequently used one, and we are familiar with it. So each experimental unit or subject is randomly assigned to one treatment condition. The subject, therefore, is nested within a treatment group. There can be a one-way layout or a factorial design. The one-way layout, we see that the treatment condition represents a single factor under study. For example, a drug at several levels, perhaps including a zero level. Treatments can be laid out in a table with just a single row. So table 5.1 shows the treatment groups in a one-way layout with K groups, treatment 1, treatment 2, so on and so forth, up through treatment K. So a one-way layout, we would have an objective to assess the effects of different levels of a factor on the response variable or variables. So the factors then could be presence or absence of a treatment, several different related treatment conditions, or several levels of a single condition or a dose response. And this is the example that we will see in just a moment. So in this case, it would be univariate statistics, one variable, of course. We would measure the relationship of one test factor to a given outcome. It would involve comparing the mean or the median value for two or more groups. So the most common tests, the Pearson chi-square, t-test, analysis of variance, or correlation. So these would be parametric or non-parametric, as we had discussed before in our flowchart on the decision-making process for experimental design and the statistical analysis to be used. So a summary of the common univariate tests is presented in the next series of slides. So for normally distributed continuous data, this would be parametric. So it would be paired or the matched t to compare paired measurements on each subject or on matched subjects. An unpaired or a student's t, the one we're more familiar with, we would compare the means of two groups of subjects. Still, for normally distributed continuous or parametric analysis, the analysis of variance, or ANOVA, would be used to compare means of two or more groups of subjects. The Pearson correlation coefficient would be used to assess the direction and the strength of linear relationship between two different measures taken on one set of subjects. For ordinal or non-normal data, non-parametric approaches are used. The median test or the rank sum test is used to compare the medians or the ranks of two or more groups. The Kruskal-Wallis one-way ANOVA is used to compare the ranks of one or more, of more than two groups. So again, the completely randomized design, we can have a factorial design, and this would be used when we're assessing the joint effect of two or more factors. So there is an advantage over the one factor at a time approach in that the response to simultaneous administration of factors can be assessed. So typically there's a low number of factors, 2, 3, or 4 at most, and this is, of course, the most common style. So with the factorial design then, we see two common ones here, a 2 by 3 or a 2 by 2 or a 2 by 3 design. And so commonly each factor is assessed at exactly 2 levels, 2 to the k design. So we see here in table 5.4 the treatment combinations in a 2 by 2 factorial study. This also could be a two-way factorial design. So the control, A alone, B alone, or A and B. And we'll see a schema of this in the potential outcomes in just a moment. In table 5.2, we see the treatment combinations for a 2 by 3 factorial design, A1 plus B1, A1 plus B2, A1 plus B3, and of course A2 and B1, A2 and B2, A2 and B3. So the statistical analyses of these becomes more complex as we add these on. So Here we see in Figure 5.1 an illustration of the interaction in a 2 by 2 factorial experiment. So we see the effect of control here, the effect of A here, and the effect of B here when they are all administered alone. We see three possible outcomes when we have the combination of A and B. In this case, A plus B caused some type of interference where we only measure the effect at the magnitude of B. This, however, can be interpreted in three potential ways. We don't know which without further experimentation. First, the effect of A might be negated, so we only see B. Or there's no effect of B other than to enhance A up to B. And the final is that we get some effect of B and A such that it only achieves the level seen by B alone. So we really don't know what it is, but we'd have to perform additional experiments to make that final determination. So in other words, this is inconclusive data other than that there's an interference. If the effect of A and B together is additive, then the actual value above control for A plus that of B, so the distance from here to here should be the same as from control to A. This would be additive. A plus B equals AB. However, if A plus B is greater than B, then AB, we say that there is a synergy. So we have a response in excess of the total of A and B. So first we would analyze the data, determine those values, and state them as such in the results, and then the interpretation, typically within the discussion section of a report, would provide that type of an interpretation as we just observed. So continuing with some common designs in biological experimentation, there can be a repeated measures design. So this means taking more than one measurement from each subject, animal, plant, cell, whatever the sample is. So more than two, so there's not just a paired comparison. For example, one of the factors being studied is time, more than 2 time points, and a measurement on each animal in each treatment group is made for each time point. We'll see some examples of this in a moment. We are not only interested in assessing the overall effect of treatment, but also the effect of time. So does the effect of treatment change over time? And then the treatment by time interaction. So the second factor can introduce a real treatment condition other than time, such as dose level, but the analysis proceeds in the same way. So here's an example of the effect of dose over time for a particular type of a drug, and of course an antagonist shown here in the final panel, and its effect. So this would be a one-way analysis of variance that would apply to this with repeated measures, because we're simply studying a dose effect or a related drug and its change over time. So we made repeated measures on the same animals in each treatment group over time. So we see the effect of saline does not become significant over time. And this first dose of this drug, 8-hydroxy-DPAT, being injected into the hippocampus, also has no significant effect over time. Finally, at the 100 nanograms dose, there is an effect, with the maximum effect occurring at about 30 minutes. So you'll see that we use this maximal effect to collect that data point from all these other treatments and another set of treatments just to evaluate the effect of dose. So that it's not a repeated measure there, but this is a repeated measure. And the approach we took was the one-way analysis of variance for each of these over time with repeated measures, and got a significant ANOVA, and then performed a post hoc analysis, a student Newman-Cool's multiple comparisons test. We compared each of these to each other and, of course, to the 0 point, and those that had the most significant different and greatest magnitude of change from the baseline were considered to be the maximal response, and that occurred obviously here even visually at about the 30 minutes. And then that told us what time point to use to make the other comparisons across the doses. So there was no dose comparison in the statistics that were performed here. Each dose was considered separately, so it was a one-way analysis of variance with repeated measures. So no change in dose, just a measure of a single factor, the effect of a single factor on a single outcome over time. So there was no analysis across all these treatments. There was an analysis of variance to determine the point of maximal effect. That same time point from each treatment group was then taken to perform a subsequent one-way analysis of variance, not a repeated measures, with the same post hoc analysis test to determine a dose effect. So the types of controls that can be used are a standard treatment condition against which all the others may be compared. So, for example, a negative control or an active control, a positive control. And I'll show an example of this in a moment. So the concurrent controls would be used versus some type of historical control. So it would be included in the actual experimental design, and it must be justified to include it or to exclude it. So negative controls are considered first. So this could be any treatment condition which would be expected to produce a response at the same level as normal or background population of experimental units under study. And it provides results at the nominal level so that the substantial changes from this level can be assessed for the experimental treatments in the study. Again, for negative controls, the subject might be used as his or her own control. This could be a phasic approach, phase 1 and phase 2. Be first evaluated under standard conditions without treatment, and then the treatment is applied and the response is remeasured during or after that treatment. So all the comparisons will be made within subjects rather than between subjects. So because the intra-subject variation is often lower than inter-subject variation, this is a sound design. There can also be untreated negative controls. So this is seen with the between treatment or inter-subject designs as a designated control group. Sometimes it's called a naive control group. There can also be a placebo control group. We saw the vehicle control in the previous example, where the saline was the vehicle or the diluent, so it was injected. Or there could have been a sham control, where the animals underwent the surgery for the intracranial injection cannula implantation, but the measurements were taken over the same period of time without any brain injection. Negative controls could also include an active control, so a condition which is expected to elicit a substantial response in the type of experiment under study. So there's two reasons for including this, and this is to validate the experiment or the test system and to demonstrate that it is performing within the limits that are expected. So we're obviously controlling bias with this approach. Is our system calibrated, basically? And it serves as the basis for comparison when a negative control is inappropriate or infeasible. So a dose selection in the dose response studies is considered on this slide. We saw a dose selection in the previous study, and we'll see an example of a rationale for an experimental design that takes this into account and how we settled on those doses. So there's four purposes for a dose response study. First, to determine if the factor under study has any effect at all on the response. Next is to estimate the parameters of a particular known model in the population under study. Next is to assess whether a particular dose response model holds relative to the likely alternative models. And finally, to select one or more possible models from a collection of candidate models. So basically this last one was part of what we were performing in our studies. We had 2 strains of rats. We wanted to determine that the same doses of a drug injected in the same area did not produce any significantly different effect between the 2 strains of rats. These 2 strains of rats did differ in their response to infusion of a drug that induces panic. We'll see that mentioned later. Intravenous sodium lactate infusion induces a panic attack, changes an increase in blood pressure and heart rate, and behavioral response, rearing in their cage, that is considered a panic response to this infusion. So we wanted to make sure that there was no difference in the response of these 2 strains to the same doses of the same drug injected into the same area. So basically we touched on all of these in selecting our doses so that we could establish a model for studying anti-panic effects of this drug. So the dose selection in the dose response studies then depends on the objective and the design of the experiment. So we wanted to find a subthreshold dose that would not have an effect in the well-known strain of rat and this other strain where we can induce a panic attack. And there's no difference in the response overall between the doses, times, and strains. And then we wanted to use that subthreshold dose to try to block the induction of a panic attack. So the overall objective and the design of the experiment is key in selecting the doses, and we'll see more of this as we go on. So a 0 vehicle dose with 2 or more additional doses would be used. It can increase linearly, increases by fold. We saw that. 2-fold and then 3-fold from 50 to 100 to 150. Or a log increasing by 10 to some power, 10 to the 1, 10 to the 2, 10 to the 3, and so forth. So here we see the 30-minute time points. We saw the peak effect at 30 minutes with the 100 nanogram dose of the 8-hydroxy-DPAT, and the decrease in the mean arterial pressure is shown here. So the saline had no significant effect. When we mixed, this is there's another data point in here. The antagonist was given with the highest dose, and it blocked the effect, so it is a causal association thereby. The 8-hydroxy-DPAT is acting, producing this response of lowering blood pressure, and heart rate was the same, by acting through the 5-HT1A receptor. So we see that there is a nice linear effect of dose here, even though I don't have the correlation. It would have to be run on that data set to verify that, but it sure has the appearance. And then this is the endogenous ligand itself, serotonin, so it does produce an effect in the same direction. So the statistical analysis, the one-way analysis of variance across this was significant, and the Student-Newman-Cool's post-hoc analysis to compare the groups showed that there was no statistically significant difference between the saline, this combination, the 50, and therefore we concluded this to be a subthreshold dose. This was significantly different from all of these, as was this significantly different. In addition, the endogenous ligand was significantly different from the vehicle control. So we established from this a subthreshold dose of a drug that can produce a blockade of the some circuit that can activate or sustain blood pressure, and that it is indeed acting specifically at the receptor that it is designed to target. So here we see an example of a rationale for a specific aim in an experimental design in a research proposal. The specificity of the effect of the left unilateral or bilateral hippocampal dentate gyrus 8-hydroxy-DPAT, a 5-HT1A agonist, injections on the cardiovascular and behavioral response to intravenous sodium lactate infusion in the SHR. So I only include the portion that discusses the rationale for the selection of the doses to be used. So several doses have been reported for injection into the hippocampus, fortunately. Maynard and Trite utilized an enantiomeric form at 0.1, 0.25, 5, and 10 micrograms per side for their study in producing anxiety-like effects. So this is 100 nanograms and 250 nanograms. So you can see we ended up in a dose range that was even lower than that. But this is an enantiomeric, so it's the mixed, so the plus or minus form. So really what dose, what effective dose of the active form is present here. So we performed tests on the enantiomer form originally. Belchiva and his co-workers used a 1 microgram for unilateral and bilateral dorsal hippocampal injections. So this is quite high. And their comparative studies showed that the right hippocampal receptors, when stimulated with that high dose of 8-hydroxy-DPAT, showed asymmetry and specificity for anxiogenic effects in the Vogel's conflict test. So again, we're justifying the site of the asymmetry, one side having an effect over another. So this led us to perform our preliminary experiments with unilateral right side injections. So we have data on right side. We're proposing the left side. Again, this is just discussing the selection of the dose. So we chose doses of 8-hydroxy-DPAT from File and co-workers' reports on intrahippocampal injections of 50, 100, and 200 nanogram doses of the racemic form. So these are basically the known concentrations or doses of the active form. The dose of a newer antagonist, BIO7413 at 200 nanograms for the same site of injection was chosen based upon their work as well. So updating the antagonist, if you will, to modernize the approaches. So in other ongoing or preliminary studies, we found that intravenous doses of as little as 1 microgram per kilogram of the racemic form of 8-hydroxy-DPAT would lower the mean arterial pressure and the heart rate in the SHR. This is the spontaneously hypertensive rat that also displays the panic attack with the lactate infusion. And of course, we're establishing control over selection bias there. A 0.6 microgram per kilogram subthreshold IV dose prevented the lactate-induced rearing, the behavioral aspect, one behavioral aspect of the panic attack, and the increased mean arterial pressure and heart rate, the cardiovascular response. So the idea we're building up to here is that we don't want an intrabrain or intraparenchymal CNS injection that would approach a total body injection that would have the same effect. So this data analysis wasn't completed at that time, but was compelling, such that we never used doses of higher than 150 nanogram because it would approach that 0.6 systemic dose. So the 50 nanogram dose injected into the right dorsal dentate gyrus only attenuated the lactate-induced increase in blood pressure. So we're proposing the next level, somewhere between the 50 and the 100, to see if it can be blocked completely. So would it still not have any effect alone, and would it completely block the increase or the activation of the sympathetic nervous system during the panic attack? And the general strategy is to test doses that do not lower the baseline levels of the mean arterial pressure and heart rate as an effect independent of the desired pancolytic effects. So you see in here that basically all of the sources of bias and confound are discussed, as well as selecting the dose. So this concludes our discussion of the